Welcome to KTU Maths, and today we are going to learn KTU Semester 2 Mathematics. In the last section, we learned this much portion of Module 1, and today we are going to learn derivative of vector function and its geometrical interpretation. You can refer 12.2 of Textbook 1 to get these portions. And what is Textbook 1? Textbook 1 is the 10th edition BLA calculus written by H. Anden and IRL Bevan. And this is the cover page of that textbook. You can take the textbook from your library and refer it. Before going into derivative of the functions, we can study the continuity a little bit so that we can understand the derivative of functions. A function is said to be continuous at x equal to a means a variable, when two conditions are satisfied. The first condition is limit x tends to a, f of x exists, and the second condition is limit x tends to a, f of x equal to f of a. When both these conditions are satisfied, you can very well say that the function is continuous. If one of these conditions are not satisfied, you can say that the function is not continuous. First, you have to check the first condition and prove the first condition. If you can prove the condition, you can go to the second condition. But if you do not get the first condition, you need not check the second condition, because when the first condition is not satisfied, you can just conclude that the function is not continuous. Now you may be wondering that whether these are valid for vector valued functions also. Yes, it is valid. These conditions are valid in case of vector valued functions also. Now let us understand what the first condition means. The first condition was limit x tends to a, f of x exists, right? This means that left limit x tends to a, f of x must be equal to right limit x tends to a, f of x. Maybe some of you does not know what is this. So you can check our video in the miscellaneous playlist and watch and learn what is x left limit x tends to a, f of x equal to right limit x tends to a, f of x. Please watch our video in the miscellaneous playlist. Now let us better understand the continuity of vector valued functions by doing a problem. I'll write a problem now. Vector rt equal to t square I plus cos t by tj plus tk. Check the continuity of vector rt at t equal to 0. We can write the answer now. Vector rt is continuous when limit t tends to 0 vector rt exists, and also limit t tends to 0 vector rt equal to vector r0. If both these conditions are satisfied, you can conclude that the vector rt is continuous also. If one of these conditions are not satisfied, you can very well conclude that rt is not continuous. And this is the order of doing the condition. First you have to check the second condition, and if you find that, then only you can head to the second condition. If the first condition is not satisfied, then and there itself you can conclude that rt is not continuous. You need not check for condition 2. Now let us check it. Let us check the condition 1. Limit t tends to 0 rt exist or not. To check this condition, there are one condition. This condition is only true when left limit t tends to 0 rt, that means vector rt, equal to right limit t tends to 0 vector rt. When this condition is satisfied, you can conclude that the limit exists. If this condition is not satisfied, you can stop there and conclude that the limit is not continuous. I mean, vector rt is not continuous. Now we can check this one. First we can check left limit t tends to 0 rt. In the former video, I have told you that we can check the limit of a vector valued function by giving the limits to its component functions. I'm going to do it here. I am giving the limit to its component functions plus limit left limit t tends to 0 cos t by tj plus left limit t tends to 0 tk. We can find these one by one here. First we can put a number so that it will be visible in the screen. Before going into this, you please stop here and watch our video in the miscellaneous playlists. It is named Limits Intermediate section. In that, I have discussed the concept of left limit and right limit and whether the limit exists and the continuity of functions and also differentiability. Please go and watch it and continue here. Left limit t tends to 0, t square I equal to 0i, that means 0. Now, left limit t tends to 0, cos t by t, j will be equal to minus infinity j. When t tends to 0, it gets 0.00001, like that it gets a value, and when we put t as 0 here, it will become 1, and 1 by a smallest decimal number will give a crazy big value, and if it tends to 0, it will be approximately equal to infinity. And where we got the minus sign? The minus sign we got from the denominator, because when we put in the value of minus t in cos t, it will just become cos t, because cos minus x is equal to cos x. That's how we got that. And similar to the first result, we will get the answer for this as 0. So what do we got here? Let's continue that question. We have got that left limit vector r tends to t is equal to 0i minus infinity j plus 0k. That will be minus infinity j cap. This is the answer. Now we can find the right limit. Right limit x tends to 0, vector rt will be equal to, put the right limit for each components. Right limit t square I plus right limit x tends to 0 cos t by t j cap plus limit right limit x tends to 0 t k cap. Here similarly these two terms will be 0. You can verify the answer. I will show you how this answer will become infinity j. Let us write it here. Right limit x tends to 0 cos t by t j cap. We have to put the values from right side to 0. That means if it is 0, we have to come from right side and put values that are approximately equal to 0. Let us put this value now. Then cos 0.00001 by 0.00001 will be equal to 1 by, it will be approximately equal to 1 and it will be 0.00001. The answer will be approximately equal to 1000001 and 5 zeros. Then the logic says that if this value is extremely small, then the last result will tend to infinity. Then we can write down it. Right limit x tends to 0, vector rt will be equal to 0 I cap plus infinity j cap plus 0 k cap. The answer will be infinity j cap. Now from these two answers, we have understood that left limit is not equal to the right limit. Let us write it now. Left limit x tends to 0, vector rt is not equal to right limit x tends to 0, rt. Then this concludes that the limit does not exist. The limit x tends to 0, vector rt does not exist. There does not exist such a limit. There is no limit like that. So we can conclude that the limit x tends to 0, vector rt is also not continuous. It is because this condition was not satisfied in the question. Okay, now let us go to the next section. Now we are going to derivative of vector valued functions. But if you want to further understand the limits, the continuity and the differentiability of functions, you may check our video in the miscellaneous section. It is named Limit Intermediate. You can check that video and learn how to find the limit, the continuity and the differentiability of normal functions, and it can be adapted to vector valued functions. A vector valued function is said to be differentiable if this limit, I will write it down now, limit h tends to 0 r of t plus h minus r of t by h. If you can find this limit and prove that this limit exists, you can very well take that value and say that it is the derivative of vector rt. It is the derivative of vector rt. Now you do not need to do this in vector valued function. Do this if it is necessary. But in most of the function, you will only get questions to find the derivative, not to prove the derivative like this. Now we can find the derivative of one function so that you will better understand derivative of vector valued functions. Okay. Vector rt is t square I plus e raised to t j cap plus 2 cos pi t k cap. Now in this question you will have to find derivative of vector rt. You will have to find this. Now let us find it. Normally what would you do with real valued function? You will take the derivative of each of the components. Behind this question is the assumption that this is valid. That means that this limit exists. By assuming that, and it is true, we will straight away do this question and we will neglect this proof. Okay? You will have to find it. Now let us find it. d by dt of t square I cap plus d by dt of e raised to t j cap plus d by dt of 2 into cos pi t k cap. You must first go and study the basics of differentiation and then come and solve this. Maybe we will put a basic class of differentiation in the miscellaneous playlist and you can watch that video there. Now this answer would be 2t I cap plus e raised to t j cap minus 2 into sine pi t, and you would have to differentiate that angle inside also, then it will be pi k cap. We can rearrange the answer and write it once again. T I cap plus E t j cap minus 2 pi sine pi t k cap. And this will be the answer of derivative of vector RT. I hope you understood this problem. This problem was pretty bit simple, and this is how you solve derivative of vector valued functions. Before going into the geometrical interpretation of derivative of vector valued function, let us look at one more problem to make us familiarized with this, and we can get into the geometrical interpretation. Now let me write a question. The question is vector RT is equal to tan inverse t I cap plus t into cos t j cap minus 2 root t k cap, and you will have to find the derivative of vector RT. Now let us find it. As in the previous question, you will have to take the derivative of each of the components separately and couple it. Now let us do it. Derivative of vector RT will be d by dt, that means derivative of tan inverse t I cap plus derivative of t cos t j cap minus derivative of 2 root t k cap. We can solve the problem. The derivative of tan inverse t will be 1 by 1 plus t square I cap plus the derivative of t cos t will be, I will do it here. We would have to do the multiplication rule. First into the derivative of second plus second into the derivative of first. So this is the answer. Sin t, t sin t. So this will be the answer. Minus t sin t plus cos t. And it can be rearranged and written as cos t minus t sin t. This will be the answer that is put here. So cos t minus t sin t j cap, and we would have to do the derivative of 2 by 2 root t. We can cancel those 2's and write the final answer here. 1 by 1 plus t square I plus cos t minus t sin t j cap minus 1 by root t k cap, and this will be the final answer of this question. I hope you understood it, and as you can see here, you need to have some basics of derivative of function so that you can adapt in vector valued functions also. Maybe some of you might be waiting to hear the geometrical interpretation of derivative of vector valued function, but we cannot straight away go into that. We must first understand the geometrical interpretation of things we have studied in the previous video. First, let us look at some portions that we have studied in the previous video and understand its geometrical interpretation thoroughly. Now, this is the thing that we have studied in the previous video. We have studied that a vector valued function RT can be written as xt I cap plus yt j cap plus zt k cap. Now this can be parametrically written as xt, yt and zt. And what is xt, yt and zt? These are the terminal points. Here I have plotted it in the graph. These are the terminal point. Terminal point means end point. And what I mean by initial point is the starting point, and it is origin. Every vector valued function RT will have the starting point, origin, and will have some terminal point. Here the terminal point is xt, yt and zt. Now by substituting each values of t, we can get infinite number of terminal points. We can get this terminal point, and we can get infinite number of terminal points, and by joining those terminal points we can get a path like this. And this path in vector valued function is called parametric curve. I will write it down. Parametric curve. It is the path traced by the terminal points. Now this is the geometrical interpretation of vector valued functions. And by two vector valued functions, we can get even a line segment. That's what we are going to study in the next. Now here we will study some basics of vector form of a line segment in 3D space, because this portion is similar to that of derivative of vector valued functions, and the geometrical definition of both are very much intertwined. So let us study it. We know that vector r0 and vector 1 are vector valued functions because it starts from the origin 0, 0, 0 and also have terminal points like this. This terminal point can be understood as x1, y1 and z1, and again this terminal point can be understood as y0, x0, y0 and z0. And with the help of summation of vectors, we can find this vector also. That's what we are going to study next. Please look at this graph now. What we have here? We have two vectors, vector v and vector w. And with the help of summation of vectors, we have v plus w vector. And it is taken from the basics of parallelogram law. Please notice that we can construct a parallelogram based on the vectors and write the diagonal vector as the sum of the vectors. Now let me adapt these two information to my problem. I have a vector valued function r0 and a vector valued function r1. It is joined in the tail portion, but look here. The vectors are not joined in the tail portion but joined in the head portion. So I will adapt it now. So this vector, please note the sign of the arrow. So this vector can be understood as r1 minus r0. Is it true? Let us verify that. Let us make it into our basic portion. We have v vector here and suppose that we do not know the vector here, and we will write that w minus v1 here, and by taking the basics from this portion, what will we get here? We will get w here. That means w minus v plus v. We will get w vector here, and that's how I concluded this. And let us take this to our problem. Now I will write what is the vector from the first terminal point to the second terminal point, and I can write this vector as vector r1 minus vector r0. And it is true by the summation of vectors. Since we have studied all this, let us progress to the vector form of a line segment. And what is the line segment that is mentioned here? We know that the line segment mentioned here is this one, and this line segment can be written in a vector form, and that's what we are going to study next. But before that, we need to have some more basics of vector form, and we can understand that by referring to this diagram. Suppose that there is a vector that we know, and that vector is called v, and its terminal points are a, b and c. And we also know another vector, that is p0, and its terminal points are x0, y0 and z0. By knowing these 2 points, we can have the vector form of a line joining p0 and another point. This point is unknown here. The p point is unknown here. So we can write the vector as p0p vector can be understood as the scalar multiple of v vector. And what is p0? We know that p0's terminal points are x0, y0 and z0. And what is p? P is unknown here. So this is the vector form of that line segment that I have shown in the second diagram. Now I will write all this in parametric form. This equation can be written in parametric form as x minus x0, y minus y0 and z minus z0. This is the parametric form of this vector because the first terminal point is the terminal point of p0 and the second is the unknown terminal points. Here I will show you that a line segment with points x1, y1 and z1 and then x2, y2 and z2 can be written as x2 minus x1, y2 minus y1 and z2 minus z1. That's only what I have applied here to find the parametric equation. And we can write the parametric equation of the second as t into a, t into b and t into c. This is the parametric equation of the second. Now we can equate both. X minus x0 is equal to ta, y minus y0 is equal to tb and z minus z0 is equal to tc. Here we can find the unknown points, that is x. X is x0 plus ta and y is y0 plus tb and z is z0 plus tc. Here we know the value of x0, y0 and z0. We know the value of a, b and c, and we also know the value of the scalar multiple t. Here t is any number. I hope you understood all this. This is the equation. I will repeat once again. This is the parametric equation of the line segment. Now we are going to apply all that into this diagram from the start onwards. I have just told you from the start onwards previously, but I'm going to repeat it once again so that you will understand this concept clearly. And we have R1 and R0 as vector valued functions with origin 0, 0 and 0. We have two terminal points and we can find the vector that joins the two terminal points and the direction up to R1 as R1 minus R0. At this line segment, please look here, this line segment can be written as the vector form of the line segment can be written as scalar multiple into the vector that we have got here. And now do you understand what is written here? Exactly the same thing. Because in this vector, one terminal point is known and the other terminal point is not known. The terminal point of vector r is unknown. Whether the vector r be this or the vector r be like this, both would have the same equation because one of the terminal points is known and the other terminal point is not known. This we can compare with the previous portion and write as a scalar multiple of the vector we know, that is r1 minus r0, and that's what we have written here. And we can further write L as vector r0 r. That means vector r0 to r, whether r be here or whether r be any other point in the line segment in the same direction as that of vector r1 minus r0. It should be in the same direction as this vector. Otherwise, we can't write it as a scalar multiple. Here, vector r0 r can be written as t into r1 minus r0. And what is vector r r? By taking insights from the parametrical forms that we have studied previously, we can write this vector as the unknown points vector is equal to the known points plus scalar multiple into the vector we know. This equation x is equal to x0 plus ta. Here a was a vector that we have taken as a reference. In the previous section, we know that the vector was vector v and we have taken a as a point from there. This was from r0 vector and this was an unknown point. And we have successfully adapted this portion into what we need here. And this is the vector form of the line segment in 3D space. I hope you understood this portion. Now we have finally arrived at the derivative of vector valued function in 3D space with its geometrical meaning. We have already looked at the derivative of vector valued function in the previous sections, but here we are going to look at it in a geometrical perspective. and this is the diagram you need to check. Here C is the parametric curve, we have already learned that, and RT is a vector valued function, we have already learned that, and the derivative of RT can be understood as a tangent in the curve. The derivative of vector valued function RT can be understood as a tangent in the parametric curve at the terminal point. The value of t there will be known. T is the thing that we have to substitute because we have already done that. Because we have already learned that vector valued function like RT is governed by t and its derivative will also be governed by t, and we have to put the value of t at the terminal point. We have looked at the geometrical meaning of the derivative of vector valued functions, and here we are looking at the geometrical side of the tangent line of that vector. And in the previous portions we have studied about the vector form of a line segment. Similarly, this tangent vector can also be described in terms of a tangent line. Here you know that vector RT0 is a vector valued function starting at the origin and has a terminal point which is x0, y0 and z0. In the previous section we have also learned that the derivative of a vector valued function is tangent to the parametric curve in that point. That's what we have drawn here. It's vector RT is equal to vector RT0 plus t, that is a scalar multiple, into the derivative of vector RT0. And this is some point in the tangent line. This is a point in the tangent line. And we already know one point, that is this, and the other point can be found out by this equation. And if we know RT, we would also know the derivative of it. This equation is the equation of the tangent line, and you need to study it by heart. To clearly inculcate the concept in your mind, I will also write the line segment equation that we have studied previously. I will write it now. The line segment equation that we have studied previously was vector R is equal to vector R0 plus t into R1 minus R0. R1 minus R0 was the reference vector V. So what we have here? We have applied this equation into this problem and derived at the equation of the tangent line, and you need to study this equation by heart. By doing so, you can do many problems in this section. Now let us look at some of the problems that are likely to come up. Now we will look at some questions that are likely to come in the derivative of vector valued functions section. I will write down one question now. Find the parametric equation of the tangent line to the circular helix x is equal to cos t, y is equal to sin t, and z is equal to t, where t is equal to t0, and use that result to find the parametric equation for the tangent line at the point t is equal to pi. Now what we have here in this question is interesting. We are already said that this is the parametric form of a circular helix. It's also given that t is equal to t0, and we have to use that result to find the parametric equation of what? Tangent line at t is equal to pi. Now let us do it. First we can write the vector of the helix. The vector will be sin cos ti plus sin tj plus tk. Here we have to put the value of rt0. rt0 will be cos t0i plus sin t0j plus t0k. The derivative of it will be minus sin t0i plus cos t0j plus k. The tangent line equation would be rt is equal to, we have to write rt0 first, cos t0i plus sin t0j plus t0k plus t into, we have to write r dash t0 minus sin t0i plus cos t0j plus k. We will simplify this answer now. rt is equal to cos t0 minus t sin t0 I plus sin t0 plus t cos t0j plus t0 plus tk, and this will be the equation of the tangent line. Now that we have got the equation of the tangent line, we can conclude that the parametric equation for the tangent line, would be at t is equal to t0 would be, we have already found that cos t0 minus t sin t0, comma sin t0 plus t cos t0, comma t0 plus t. This is the parametric equation of the tangent line at t is equal to t0. Then what will be the parametric equation of the tangent line when t is equal to pi? We have to just change the t0. It would be cos pi minus t sin pi, comma sin pi plus t cos pi, comma pi plus t. This would be the equation. And now we will simplify this. Cos pi is minus 1 and this term would be 0 because sin pi is 0. Then after simplification we will get minus 1 comma minus t comma pi plus t, and this is the final parametric equation of the tangent line at t is equal to pi. Now we can look at another question and solve it. r1t is equal to tan inverse t I plus sin t j plus t square k. Vector r2t will be t square minus ti plus 2t minus 2j. It is not j, it is j cap, sorry. Natural logarithm of t k cap. Okay, now we have to find the angle between the tangent lines of these two functions. We will find it now. First of all, we need to find the tangent line of these two functions. The tangent line would be, the parametrically it would be 1 by t square pi. It is the derivative of tan inverse t. Now sin t would be cos t, and t square would be 2t. This is the parametric equation. And the second derivative would be 2t minus 1, comma, 2, comma, and 1 by t. This would be the equation. We have to find the acute angle between the tangent lines of these two vector valued function at the origin. Now at the origin, what would be the value of t here? The value of t would be t is equal to t0. This would be the value of t at origin for this vector valued function. For the second function, what would be the value of t? T would be 1, because 1 minus 1 would be 0, and at the origin both the vector valued function will have different values. Now we can substitute that. At t is equal to 0 and at t is equal to 1 would be, t is equal to 0, it would be 1, 1, 1 and 0. The second one would be 1, 2 and 1. That means I plus 2j plus k. Now we have to find the acute angle. We have to substitute in the equation. Cos theta is equal to the dot product of the first vector 1, 1, 0. I am writing the parametrical form 1, 2, 1, and then again the magnitude of this vector 1, 1, 0, and the magnitude of the second vector 1, 2, 1. By calculating this, we will get 1 into 1, 1 into 2, and 0 into 1. It would be 1 plus 2 plus 0. And the magnitude of first one would be root 1 square plus 1 square plus 0 square. That would be root 2 into, it would be root 1 square plus 2 square plus 1 square. It will be 6, root 6. Then the answer would be 3 by root 12. This would be the answer. We can further reduce the answer to root 3 by 2. We finished there, because we have only found cos theta is equal to 3 by root 12. Now we would have to simplify this. We can write 3 into root 12 can be factorized as 2 into 2 into 3, and it will be 3 by 2 root 3, and root 3 and 3 can be cancelled to root 3 by 2. This would be the answer. Then theta can be found out by taking the inverse of cos. Cos inverse root 3 by 2. Cos inverse root 3 by 2 would be 60 degree, that is pi by 6 radian. Stay tuned for unit tangent vector, unit normal vector, and binormal vector, because that portion is the second part of what we have learned today. And if you do not know the basics of vectors, limits, or something like derivative of functions, we will upload videos on that too in our KTU Maths miscellaneous playlist. So watch that also.